Good morning, everyone. Today is April 20th, 2019, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. And we meet here every Saturday on Fuse. So please go tell all your friends. It's the most interesting thing that's happening on Saturday morning. And come visit our website at naturalphilosophy.org where you can join us. And you can also find us in social media, on Facebook, and in YouTube. And you can help us out by joining Basecamp, which is hq.naturalphilosophy.org. So we have our rules of conduct here. Let's keep everything civil and to the point of science. And if you have a camera, please turn that off unless you are speaking. And also, if you're not speaking, please make sure to mute your microphone. We have our upcoming conference in June, apparently only 2 months away. So please start thinking about that if you'd like to go. And we'll be featuring Dr. Gerald Pollack as our speaker. So today, I thought we would be discussing a little bit about polarization. And I saw some very early experiments by Heinrich Hertz about basically the beginnings of radio and how those radio waves were transmitted and what polarization looks like in those early experiments. Because when we look at polarization through, say, polarized lenses in our sunglasses, we really can't see what's going on. So I thought it was interesting to go and look at this earliest experiments. So let's see here. So I have this paper here. You can get this paper freely on Google. It's called The Principles of Wireless Telegraphy. Okay? So this is the section on polarization. So the way he showed that is that he made this radio transmitter, which is a spark gap radio transmitter, and it just consisted of two small balls at the ends of long straight wires. So here we have a diagram of, like, on the left hand side would be his transmitter, and he's got this like shield behind it to focus the waves. And so what he found was that the waves that are generated by this simple setup are polarized in the sense that on the right hand side he has a receiver, and on the receiver also has a similar spark gap on the other side, so that if there was a spark on the left, if it was received by the receiver, you would also see a spark on the right-hand side. And what he found was that when the receiver and the transmitter were oriented the same way, then you could easily see the signal being transmitted, and that was like the first radio waves being transmitted. But if he took that same thing and he rotated it 90 degrees, as is shown in this picture, then there was no reception at all. You would not see any sparking. So that is an example of polarization, and it's the polarization of being able to literally transmit electricity across this gap. And you can see that very viscerally that there's actual electricity that creates a spark gap to signal that you have received power. And that power is pretty obvious. This is I thought this would be very, very simple, obvious kind of demonstration of radio polarization. So there is something about the orientation of the radio waves that causes this. And this is what basically polarization is. It's not so much like we see a blocking with like our sunglasses, but it's really the ability to receive waves which are oriented in a particular direction. So it would seem, for the most part, that the best transmitters and receivers happen when you have when they're built the same way. So, like in this case, the wave is best received when the receiver is built exactly like the transmitter and it is oriented in the same way. And then the worst receivers are the ones which are oriented in a completely different manner, like at 90 degrees. So there's something about the wave that makes it so it can't be received just by orienting it 90 degrees, even though it's the same distance apart. It has the same reflectors. You'd think it'd be receiving the same amount of power from the receiver either direction, but we have this very, very sharp behavior where when you rotate the receiver 90 degrees relative to the transmitter, that we don't receive anything. So that's an interesting demonstration of polarization. Now, the other interesting thing that he did was that he made this grid of wires. It's literally just a grid of wires. And he hung it on this wooden frame, as shown in this picture here. And he put that between his transmitter and his receiver. So in this picture, since the receiver and the transmitter are oriented in the same way, you would easily, without anything between it, receive the signal. So but what he did is that he went and he stuck this wire grid between them and then turned it around to see if that would make any difference. So the grid could have been either horizontal, which is perpendicular to the transmitter, or it could have been vertical to the transmitter. So I was kind of curious. Does anyone have any ideas or guesses as to what would happen when you do this? So maybe Harry, did you have a guess as to what it'll do if it's horizontal or vertical? What would you think it would do? No? No guesses? Maybe Bob, you'd like to have a guess as to what would be the effect of the wire grid? No? No one wants to guess?
That's right. Yeah, unfortunately, I'm on my cell phone this morning, not at my PC and traveling, so I can't really participate in this week's discussion, but I am here to listen.
Okay. Now, I suppose you could kind of guess that if you have this grid, and if you think that the wave goes up and down because the transmitter is basically oriented in a vertical direction, that you might think that the waves are like a rope, like waving a rope. So you would think that if the grid is in the same direction as the transmitter, that would allow the waves to slip through. I would think. It's one way of intuitively thinking, and that's often how it's explained, that it's kind of like a rope through a picket fence. So if the picket fence is in the same direction as the transmission, then it should go through. But actually, it turns out to be quite the opposite. That actually, when the grid is oriented at 90 degrees to the transmitter, that is actually transparent, that the waves travel through that setup without being diminished. But paradoxically, if the grid is actually oriented in exactly the same direction as the radio transmitter, that actually completely blocks the signal. So that seems a little bit strange. So, but there is an explanation for that, and the explanation which is generally given is that the wire grid, when it's oriented in the same way as the transmitter, actually also acts like a receiver, right? So it's in the best position to receive the signals, and because of that, electricity actually starts running up and down the length of these wires. And this kind of polarizer is called a wire grid polarizer. And because they're saying that because the electricity is allowed to run up and down the length of the wires, it actually gets absorbed, or in some cases, I believe they say that it actually probably starts to retransmit and actually reflect the signal. But this is an interesting, very simple, totally mechanical polarizer that you can basically see the entire insides of it. It's all macroscopic and nothing mysterious about it. We can see that a grid of just vertically oriented wires is capable of blocking the radio signal that would somehow get through. So that's all very interesting. And the question is why, right? Or what is the nature of the radio wave such that this kind of behavior happens? So now we'll kind of leave the basic experiment here and more get into speculation as to what the heck is going on here. Now, the typical explanation for polarization does usually show these pictures of waves that are like I said, like on a rope. So let's go look at one of those. Go find the wiki page on this, the source of truth for everything. Polarization waves. Let's see here. Is that what we're looking for? That isn't exactly the page I'm looking for here. Polarization. Close enough. So oftentimes the wave is kind of displayed like shown here with time-varying electric and magnetic fields. And I think Hertz himself had some things to say about it. And I think that probably our conventional view of electromagnetic waves is actually highly influenced by what Hertz said. But going back to the original pictures here, I'm going to present another different way of thinking how this might work. And of course, this will just be my speculation, but this is what I came up with recently to try and help explain what's going on in these situations here. So when you have a radio transmitter, it always has a certain shape. So in this simple case, the shape is basically a straight up and down rod. And if you were to think that you were to take this rod and think of it as being in a fluid, and you were to just vibrate that rod, it would create a wavefront that's basically the same, that would be the same shape as the rod itself. So if you can imagine, you have the rod and it's vibrating, much like a speaker would vibrate, and you imagine the waves that would come off of that bar.
And it doesn't vibrate like a speaker vibrates. So
I'm
wrong
just asking you to
assumption,
imagine.
wrong conclusion. Your whole analysis now just fell to pieces. Sorry.
Well, I'm just asking you to imagine. Once again, this is speculation.
Well, we don't speculate. We use facts. It doesn't vibrate like a loudspeaker does because it's not a longitudinal wave. Okay. And so you're trying to argue that these antenna theory is a well-established theory. There's tons and tons of textbooks. Have you ever read one?
I've read plenty of textbooks.
Stop. Let's move on to another topic.
Well, as the presenter here, I have the right to present my theories. And if you interrupt me, I will.
I just proved your theory was wrong, Franklin, because you never read an antenna book and you don't know anything about what you're talking about. So why are you inflicting us with this nonsense?
Because it's a possible way
that makes no sense at all. Your theory makes no sense. Your theory is based on an ignorance of electromagnetic theory. You don't know anything about antennas, and you're just wasting our time talking about this.
Well, I would beg to differ. Once again, here at the CNPS, we welcome all viewpoints, and I would ask you to let me try and explain what I think is going on. Now, it may be wrong, but then we can discuss that. That's perfectly fine.
It is wrong, Franklin, so why would we discuss something that's wrong?
Because
you've never read an antenna book.
It's wrong.
Have you ever read an antenna book? No. So why are we talking about something you know nothing about?
This is
nothing about this topic. Why are we talking about it?
Well, I would appreciate you just simply stop trying to shout me down, which is what you're doing.
Well, you're imposing on us a stupid theory, okay?
I don't think
and there's no point in talking about your nonsense theory, which is wrong because you don't know anything about antenna theory. You don't know anything about EM theory. So why are you talking about this?
Because I believe most of EM theory is, of course, completely wrong.
Well, you don't know that because you never read a book on it.
But we do see the experiments. That's why I bring up Hertz's original experiments.
You never read a book on any of this, Franklin. You know nothing about any of it. You never read a book. So we're talking about you're giving us your expert knowledge when you know nothing.
Let's see here. Can someone else help me out here? Because obviously Harry's not going to let me speak. It's like, pal, are you interested in finding out how radio waves might?
I let you speak until you said an antenna is like a loudspeaker, which is all of the facts in all of the EM textbooks say is not correct. So why should we proceed any further?
Because the possibility that,
possibility, Franklin, your theory is based on nonsense.
The thing is that
comes out of your mouth is nonsense.
The thing is that every science book used to say that the Earth was at the center of the universe, and that anyone who would say that it is not is nonsense, and they would be shouted down. Now, in the case of EM physics, I believe a similar thing which has occurred. and that everyone
And
believes
you
that
know
the Earth.
nothing about EM physics, Franklin, and so that entitles you, the fact that you know nothing about EM physics entitles you to say EM physics is wrong, right? That's your thesis.
In fact, it is. So,
Okay, so we know that you're
Sorry, sorry.
pontificating about something you know absolutely nothing about. Thank you.
Yes, and then maybe it's I just ask you to just let me speak. All right, just have the common courtesy of anyone else coming here with any other crazy theory. You know, it's fine. We let them speak. So I just ask you to give me the same courtesy, right? Now, just let me explain. Now, if you think that
Now
things
we
are wrong,
understand now, Franklin. We understand that you know nothing about what you're talking about because you just admitted that you don't. So I see no point in really proceeding along in this discussion because you said you know nothing about EM theory and you know nothing about what you're talking about. You're going to pontificate about a theory which you know nothing about. Why are we wasting our time doing this?
because what we do know are the experimental
Because
results.
you're the moderator and you want to waste our time. Let's not waste our time listening to your silly stuff. This is silly, okay? It's silly, and it's a waste of my time, and it's a waste of other people's time.
Well, Harry, if you feel that way, then please drop off the conference, okay? There's no one who's telling you to be here. If all you're going to do is be disruptive, then please drop off the conference.
I'm not being disruptive. I'm telling you that there's no point in listening to somebody pontificate about something that he knows nothing about.
I know about the experiments. Science is about
I don't know anything about this. Okay,
well,
an EM antenna is not a loudspeaker. Okay?
Yes, it is a loudspeaker. It is totally a loudspeaker. This is one of my basic principles of making
Thank you for showing us you don't know what you're talking about and your theory is completely wrong.
No, it is not completely wrong. So, Harry, if you're going to be this way, then I would ask you please drop the conference, okay?
No, I really don't want to because you're wasting our time talking about nonsense. You come on here and you use your position as moderator and you talk about this is not a subject that we want to talk about because it's nonsense. It's your silly pet theory.
We're talking about radio waves.
No sense whatsoever. You're wasting our time, Franklin.
Harry, I'm going to have to ask you to please leave the conference, okay?
I'm going to have to ask you to please talk about something that people care about. I don't care about listening to a theory that you don't know about. You don't know anything about EM theory. You don't know anything about the subject, and you're pontificating a silly, stupid, ignorant theory based on your silly, stupid, ignorant ideas that you're imposing on the rest of us as moderator.
So, Bill, can you help me out here? Can we, are you interested in hearing about polarization and how it might work, or is Harry right?
There are two types of electromagnetic radiation. There is transverse and longitudinal. Longitudinal was denied by the followers of Maxwell, and they tried to get rid of that. And sound waves are longitudinal. So when most of the experiments that are done, you'll find in electromagnetic textbooks, the electromagnetic waves are transverse. And so when you're talking about polarization and things like that, many of the devices that we use to separate out certain polarizations are designed primarily for the transverse radiation. So that's kind of a little bit of a background there. In my work, I deal with both the longitudinal and the transverse, and the longitudinal is related to light. It's the
the question here that I'm trying to get some motivation is like, can I go on and explain how I think things work? Now, obviously, in my work, I think that the longitudinal picture of the wave is probably more accurate representation of what's going on versus the transverse. And in fact, the entire notion that electromagnetic wave has an electric and a magnetic field, I believe, is a completely wrong notion, that no magnetic or electric field has ever been measured in a time varying fashion as is.
So you're basically asserting out of your ignorance. We already know you know nothing about EM theory. You know nothing about what you're talking about. You never read a textbook on EM theory. You know nothing about antennas. And now you're telling us that you are in a position to criticize that?
Yes, I'm in a position to criticize that.
No, you're not, Franklin. You're not.
How can you criticize that? You haven't read a textbook. That's
Bob, we're having a little bit hard time hearing you there.
Oh, am I?
Are you speaking to your phone directly?
Sorry, the mic turned on accidentally.
Well, you're trying to say something anyways. Okay, but
so Bill,
you know,
is a dipole antenna a source of longitudinal waves?
No, believe it or not, longitudinal waves are only made by capacitors.
Okay, so what Franklin says is based on a wrong premise.
Yeah, well, it could be, or it could be that it's very difficult, since we can't physically see a wave, to see what it's actually made out of. It could be
I'm sorry, Franklin. I mean, you said that the dipole antenna was like a loudspeaker, and I refuse to accept that. Okay, so your whole presentation falls apart. Okay, because you made a wrong assumption. Sorry.
Well, what if I change that?
Something else.
Harry, let's just change it to something about that the shape of the radio wave that comes out is the same shape as the transmitter, right? So if you have a rod-shaped transmitter, the propagating wave, if you had a detector, would also look rod-like. Would that be okay?
I don't think that follows, Franklin. And that's just your based on your silly misunderstanding of physics based on the fact that you've never read a textbook on antenna theory, and you never read a basic EM textbook either, and you know nothing about this topic, and so you're just basically making up stuff based on the fact that you don't know anything.
I'm making up hypotheses to try and fit the experimentally observed result, like this experiment with
Hertz. Well, that's what all the textbooks have done, Franklin, which you have not read any of. Okay, so all of EM theory and what's in all of the textbooks is based on doing experiments, and these things are they're proven every day in practical electrical engineering and radio engineering. And so people who write these books know what they're talking about because they've worked with antennas, they've worked with radio, they've done all these things year after year after year after year, like I have. Okay, I made a living doing this. Did you?
No, I haven't.
So that doesn't qualify you to talk about this subject, does it?
Well, I didn't say I was qualified, but as...
Well, you're obviously not, based on the silly things that you're saying. Okay, if we're going to talk about something and we're going to talk about experiments, let's at least talk about something that's interesting and not based on your pet theory.
But this is all we do in the CNPS. We always just talk about our pet theory, so that's perfectly fine.
I don't want to talk about your pet theory because your pet theory is wrong. Your pet theory is wrong, Franklin.
Well, that's great.
You've been told this for 10 years, for as long as I can remember, since the Glenn Baxter days. Your pet theory is wrong. Accept it. Move on.
Yeah, but you need to say why it's wrong. This is the problem, is that you say it's wrong, but you don't ever explain why, other than it doesn't.
I've told you
It doesn't match
10,000
the
times
mainstream.
why it's wrong, Franklin. You just don't accept it. So let's talk about the magnet going down the copper tube.
Look, Harry, I'm just like anybody else who has a topic. I want to present on it. Now, it could very well be wrong, but you know, it's people's right to do that. And if you don't like the topic, then you can drop off.
You're wasting our time, Franklin. You're wasting our time.
Yes, well,
you have an hour to talk about this. We've already spent 33 minutes talking about nonsense. Let's talk about
we haven't. We've spent like 15 minutes just me arguing with you, just trying to be able to just discuss my theory.
Because you refuse to accept that your premise, okay, that an antenna is like a loudspeaker is false. Okay, it's a false premise. Sorry.
Okay, I'm going to give people a chance. So if you don't want me to continue talking about polarization, then please speak up.
You can talk about polarization as long as it doesn't include your false premise that an antenna is like a loudspeaker.
I'm giving people a chance. Okay, so no one seems to have objected to me continuing to explain my theory. It may be crazy, it may be wrong, but it's going to be different, okay? And different is interesting. So,
it's not, Franklin. It's a waste of people's time to talk about something that we know is false.
Harry, I'm going to have to ask you to be silent. Otherwise, it's
false already, Franklin. Why are we talking about something that we know is false?
So Harry, I'm afraid I'm going to have to manually mute you so that you don't interrupt the meeting anymore. Okay, you've become disruptive, and I have to mute you. Okay, so please, if the topic doesn't. Well,
Franklin, that just shows that you can't take it.
Please leave. If you're just going to be disruptive, I'm going to have to mute you or drop you from the conference. Okay.
You're a crappy moderator, Franklin.
At this point, you're just being disruptive, okay?
No, I'm not. I'm telling you, you're being an idiot.
Okay, I'm sorry I had to do that, but Harry was just being disruptive. He's not allowing the conversation to go forward. So I have to drop him from the conference. I really don't like doing that, but there's just really no way we can go forward with him doing that. All right, now, and everyone else is welcome to either stay or go. But I'm going to try and explain what Heinrich Hertz saw in his experiments here to explain what's going on with polarization. Now, the last thing I said was that the shape of the radio wave is going to basically follow along the shape of the transmitter. So while Harry seems to be very objective against the idea that a radio transmitter acts like a speaker and is received basically the same way, I would say that because as a physicalist, I like to relate things to things that we actually can physically see. So we can physically see like how the action of a loudspeaker works, and all it does is it pushes in and out, it compresses a medium in and out, and that compression is able to push against the atoms of anything that's sitting in the room, including a microphone, and that causes the same sympathetic kind of vibrations to occur in the receiver. So what I'm going to suggest is that, you know, your radio wave is like, your radio transmitter is like a rod, say like this pencil here. So when you start putting this in oscillation, it generates waves, and those waves are like the waves that are heading towards a beach, right? They would be vertically oriented, right? So you have to wonder what would be the best kind of thing to receive these vertically oriented waves. And so the best thing that you could use to receive those waves would be another receiver, which is of the same shape. Because when the wave comes, and it will hit the full surface area of the receiving antenna. Now, if I turned it this
Franklin,
way, if I turned
I have a question for you.
Sure.
With a normal loudspeaker, it vibrates in a certain direction, opposite to the plane of the speaker itself. But with your wire, which is just a pole basically, and you're applying your voltage or whatever it is that's going to make it vibrate, how do you know which direction it would be vibrating? With the speaker, it's because of the magnet causing the paper of the loudspeaker itself to vibrate back and forth in a certain direction. But I see no way that you could control a rod like that to vibrate in any particular direction.
Well, the way I would see it would be like if you had a long, long twisty balloon. And what you do is that you're either adding or removing air from the long twisty balloon, which is like a rod. And that expands the entire balloon all the way around in all its dimensions as you oscillate it. So actually the wave would be going in all directions. This is kind of the way I think the actual transmission actually happens, and that what happens is that the voltage varies, and that's basically just electron pressure. And if you figure that your metal rod is just got all these free electrons on it, and that when you increase the pressure, that literally forces the electrons out of the surface. And it would do so in every direction, in every, that represented the surface of the metal. And so what you're actually seeing—
what you're talking about, that's not how an antenna works. Why don't you read an antenna book? Okay?
Okay, so once again, I had to get rid of Harry because he's being disruptive. Okay, now the thing is—
Franklin, you don't know what you're talking about. That's not how an antenna— Why don't you read a book? Oh, Franklin, you're gonna cut me off here because I'm telling you you don't know how an antenna—
Now I'm cutting Harry off because he's not asking any legitimate questions. Like Carl has asked a legitimate question about how does the wave compare with the speaker. That's a perfectly legitimate. Versus Harry, which is just saying, I'm wrong, I'm wrong, I'm wrong. He's not giving any explanations as to why I'm wrong. It's completely not constructive. Okay. So Carl, did I address your concern there?
I'm not satisfied with the answer, but you tried to answer it.
Okay. So going on.
I'm sorry, I was muted. Was I muted?
No, we heard you.
Okay,
You just weren't satisfied with the answer.
Okay, all right.
But I would be curious as to, why you weren't satisfied with the answer.
It just, I would think that a oscillation similar to a speaker would mean the rod would be use a balloon as an example, a twisting balloon. That the rod itself would increase in diameter and decrease in diameter, which there's no way I see that happening. And the electron thing that you posited just didn't work for me. That's all.
Okay. Well, to a tiny extent, I suppose, if you consider an electron leaping the surface and then coming back as being an increase and decrease in diameter, then that would be true. This has to go with the very basics of how we think electricity turns into radio wave. So somehow the oscillations in the voltage become the same thing as the oscillation in the air as a radio wave.
Yeah, but that would require that electricity electrons specifically are flying off in all directions, kind of
No,
like
not
a Van de Graaff. You know, everything would be static.
what we're having is that we're having a compression going on.
Yeah, but a compression of what?
A compression of some ether. That there's always this controversy over what a radio wave is. And one way you could think of it is that it is a wave in a medium, such like water or air, right? Or it could be a compression, or it could not be a compression. It's something else. So if there's like nothing in space, then it couldn't possibly be a compression. And that's where we get into people who believe that, like Bill, who think that the electric field itself is fundamental, and therefore you really don't have to explain that as a compression. It's not. It can be explained in terms of just electric field variations versus a compression. So those are two differing ways of thinking about it.
You don't know anything about antennas. You don't know.
And I have to spend half my time just rejecting Henry off the meeting here. So, but Carl, you understand that there's two possibilities there. Either there is a medium or there isn't a medium. If there is a medium, then radio waves transmit in much the same similar fashion as sound waves. But there are alternate theories, but I favor this theory that the radio wave is being transmitted through a physical medium, similar to sound wave. So you understand that, right? So that's where my bias is.
Are you adverse to transverse waves?
Yes, actually, I am very adverse to transverse waves. Now, transverse waves do exist. For example, in earthquakes, we certainly see that kind of transverse motion. But through mediums, generally speaking, it's you have to think about most of the waves that we know about physically in the world, air, water, through most things is actually a longitudinal type compression wave. So I mean, I would ask you that if you believe in the transverse wave, then it must have some physical amplitude to it. So what would be the wave height of the transverseness in, say, a red beam of light? You know, what is the transverseness in that?
That is something I'm not sure about, and I've kind of wondered myself.
Yeah, so I've wondered about it, and I've basically completely rejected the idea that this whole E and B transmission of electromagnetic waves actually occurs. So that would be my radical idea that Harry so completely objects to, which is I completely reject everything that in those science books that I haven't read. That's showing me that the wave is a combination of an electric and magnetic field. Rather, for me, I would suggest that we go back to the basics and say that, well, if a radio wave acts like a wave, you know, it has these interference patterns and such, that we simply treat it the same way that we have treated every other wave, which is it's a compression rarefication wave, right? And as I said, if it is something like that, if we have a transmitter and we have a receiver, then the best receiver is that which intercepts the full wavefront, like this. Now, if we orient our receiver at 90 degrees, then we'll see that the amount of surface area that's going to be intercepted by the main wavefront is only going to be that tiny little bit that's exposed to the diameter of your receiver. So very, very little of that giant wavefront coming through here is going to be able to impact your antenna, versus if it's the same orientation, when it hits, it's going to hit the full surface of your receiving antenna. Okay.
Yeah,
You
but
guys
that belies longitudinal waves. A longitudinal wave wouldn't care.
You're saying a longitudinal wave wouldn't care?
Yeah, there's well, it doesn't seem like it to me. Like a loudspeaker, since you use that, it wouldn't care which, an orientation. It's just because it's a compression wave. It just is like a wall traveling through the room.
Yeah, it's like a wall. I mean, another way to think about this is that you're sitting on the beach and you see waves coming in, and they're coming in, parallel to the shore, right?
But see, that is because there's a surface to the water. In sound in a room, there's no surface. It's just a big, huge room. So it's like a wall of compression transmitting from one end of the room to the other end of the room. So there's no orientation to it, no vertical, no horizontal.
Well, there would still be an orientation to the actual wave front. Think of it like a wave pool. Now, I would admit that a loudspeaker in a room, that's going to produce spherical waves, right? That's going to go out from the source, spherical waves, but the shape of it would still be spherical, right?
Yes, and the further you get away, the more planar it becomes.
Yes, that would be true. But I'm saying
okay,
that...
so, and what I'm saying is, because of that, it's more planar. It's not vertical or horizontal, it's a plane.
Yes, it would be. And that's why if you had a circular transmitter, see now that the original experiments with Hertz had like a rod. That's why I'm talking about a rod. It's a rod shaped. If you did an experiment with a completely circular transmitter, then you would probably find that you can't actually find these polarization effects. I guess would be one of my predictions. So that polarization, number one, requires that you have some kind of transmitter which has a very, very flat wavefront to it. So a rod transmitter would produce this kind of very flat, kind of like waves coming at you at the beach. Now the question is, if you're a ship and you're having waves come at you, it's like, what do you do to minimize the strength of those waves? Is that if you want to maximize the wave, you go in the same, you orient your ship in the same direction as the wave, and then you get like, Poseidon Adventure, and you'll get tipped right over. Versus if you are going perpendicular to those waves, you're exposing your ship, only the bow, to the amplitude of the strongest wave. So in that way, that is also a kind of polarization, and it's kind of the way I'm saying that polarization works. That just like a ship orienting itself so that it intercepts the smallest amount of the oncoming waves, that demonstrates either you're exposing your ship to the most of the waves, or you change the orientation and you expose yourself to the least amount of waves, right? So
yeah, but since your analogy uses the surface wave on the ocean, that is your transverse wave of the sinusoidal, looking at it up and down with your magnitudes that you were asking about earlier.
I mean, that's true, but the principles is basically the same, that the energy is in the wave front, which provides a basically like a wall, and that wall has a specific vector direction. And what you're polarizing against is actually that wall of waves. And
yeah, but you have to remember that this rod antenna that you're talking about vibrating, kind of like a loudspeaker, it would be underneath the ocean, not on the surface. You have to talk about what it does underneath the surface of the water if you're going to discuss it that way.
Well, once again, we're kind of limited with the analogies here, so we don't want to get too literal. But when I'm talking about a rod antenna, now it would be more accurate to, I don't know, immerse the entire thing in water and just like spin it around, or to put like a literal loudspeaker at the bottom of it, right? So that just it vibrates it in some fashion. The important part is that the shape of the wave it produces a linear wave that is being emitted by, and is of the same shape as your original transmitter. And
but it would still be circular, going out in all directions.
Yes,
from that, which should be very wall-like the further you got away from it.
Yes, that's true.
So I don't see that you're accomplishing anything, though.
Well, if it's a wall, see, if it's any kind of curved wall, like if I have, where's my, like a battery or something. The thing is, even if it's a wall, if you change the orientation, then it's not going to all hit this receiver at the same time. But that would be an interesting thing. You would see that polarization effects may decrease as the wave becomes more planar, right? Because once the wave becomes completely planar, if it becomes just a flat sheet, then it wouldn't really matter which direction it hits the antenna. But at the relatively short distances that we're talking about, like in this specific experiment here, it would be fairly clear to see that if you have the wave that's generated like this, the best way for it to be received is with the similar kind of receiver, because the whole wavefront hits the entire surface of the receiver. Now, how much of the wavefront gets hit when I orient it at 90 degrees? Only the tiny little bit. You can't even see how much it's getting intercepted. Only the tiny bit.
It all hits. It just doesn't all hit at the same time.
Yeah, it all hits, but doesn't hit at the same time, and that is precisely the nature of polarization that I'm trying to explain here.
All right. So if your receiver, the rod of your receiver was slightly curved, bent, and you oriented it 90 degrees such that the curvature of the wall hitting it would all hit it at once, then I think you'd prove your point. Do you understand what I'm saying?
I'm not sure I understand about the curvature part.
Okay, so if your rod transmitter is basically the signals, whatever, are going out from it cylindrically, they're expanding, right? Mm-hmm. The further you get away, right? So when your receiver rod is also oriented vertically, yes, it all hits at the same time. And when you orient at 90 degrees, we agree that it doesn't all hit at the same time. But if you bend the receiver rod slightly, when it's oriented in at 90 degrees to the transmitter rod, such that the wall, the expanding wall, the curvature of it, of the transmitted energy, matches the curvature of the receiving rod. You see what I'm saying? It would all hit at the same time.
You would predict an increase.
It would hit at the same, such that it would hit at the same time, just the way it does when it's vertical.
But all the energy was distributed up and down the vertical dimension. I mean, I would think that if you do have the curved thing like that, the prediction would be that it would be better. But if you think about the energy being divided in these horizontal segments, that's still the only energy available for it to be intercepted in the the horizontal versus vertical orientation would just be that little segment that can be intercepted by the vertical bar.
The surface area of the bar that would be receiving the signal at the same time would be the same between the two of them.
I mean, you understand that all the energy that existed above your vertical bar would be missed. All the energy below your bar would still be missed. It's not a matter of...
Yes, but I agree with you. But when you have the vertical bar, all the energy to the left is missed and all the energy to the right is missed. So what I'm saying is, regardless, if you have a curved one that's horizontal, it's going to get the same amount of energy. It's just in a different orientation than the vertical one. And that would be a way of supporting what you're postulating if that worked.
Yeah, I mean, there's possible experiments. I mean, that's how hypotheses work. So it's possible. So, but that is a good and interesting comment and criticism and discussion about the possibilities. And that's all we're looking for here, just looking for some airtime and some people to, try and explain and say what the possibilities are. So I'd have to think about, okay, that whole thing about, well, it's missing the left and the right. And, that's a legitimate thing to think about. But so today, like I said, we're going to have to cut the discussion short here for an hour today. And so we'll be ending the conference now. But I thank you for participating and being more patient with me. I mean, I really didn't like having to throw Harry out of the conference, but he was just simply being disruptive. So, but thanks for coming, and we'll do this next time, same place.
So, Franklin, do you think you went beyond the prerogative of being a moderator?
Well, no, Harry was just being completely disruptive. He wasn't allowing people to speak.
A moderator always has certain prerogatives that other people don't. And I thought that you were well within your prerogative as a moderator. And if the people in power or whoever the powers be don't like your role, or if Harry doesn't like your role, he can complain to them. I mean, complaining to you doesn't do you any good because you are the properly appointed moderator.
Well, pal, I've always appreciated your support. So, but I've got a meeting to go to, so thanks for showing up.
Thank you too.